All right, so hi everyone, welcome back. Very good evening to you all. So I guess we are live now. So can someone just please confirm if I am audible? All right, so everything seems good to me. And now we are good to start the last weekly contest 184 discussion. So let's just quickly start with the first problem. And I personally categorize this entire contest to easy from easy to a medium level. The first two problems were very easy, it's just a cakewalk. And the last two problems were a bit tricky, and both the problem uses the technique of a binary search. So you just only need to find the monotonic search space, and then you can just simply apply the binary search by finding the value of low and high. So let me just share my screen. So hope the screen is visible to you. Now let's just quickly start with the first problem. So let's just go with the first problem, minimum jump, which is a fairly easy problem. So in this problem, you are given an array of integers, points of size n, and you can move from ith point to I plus 1th point in one jump, or you can move from ith point to the jth point in one jump if both point I and point j are a perfect square. And initially you are at the first point, and you need to determine the minimum number of jumps required to reach the nth point. So this is a greedy problem. So what we can do, in this case, initially we are at integer 1 and we want to reach at to the last index, that is integer 3. So first we can jump from first to second point, and then from second to third point. And here in the second sample input, we can directly jump from 1 to 4 as both the integers are a perfect square. So in this case, we just only require one jump. So I hope it is clear to everyone. Now let's see how we can solve this problem. So initially you are at index 0, and then we have the name of the problem, minimum jump. So initially you are at index 0. Okay, just allow me 1 minute. So initially you are at index 0, then we have index 1, then index 2, index 3, 4, 5, 6, 7. And let's say the value of n as 8, that we have indices from 0 to n minus 1. So what is the best greedy approach that we can apply? So let's say at index 2, we have a perfect square. Then at index 4, we have a perfect square, and at index 5, we have a perfect square. So, and we need to minimize the number of jump. And from one perfect square, we can jump onto the other perfect square number. So what is the best greedy approach? The best greedy approach is to take a jump from 0 to 1, then from 1 to 2, and then from 2, that is from the first perfect square to the last perfect square. If you are taking jump from 2 to 4, that is from index 2 to index 4, then it will not give you the best answer. So the best way is to take a jump from the first perfect square to the last perfect square. Cool. And then after this, every time we take a jump of one index. So in total, in this case, what will be my answer? Let's say I know the index of first perfect square. Let's call this as a first index of first perfect square, and the index of last perfect square. Cool. So in this case, so actually here I have written the indices. I am assuming that index 2, we have some perfect square number, and at index 5, we have some perfect square number. So these are not the values, these are the indices. So if I know first and last, then my answer will be first. Because of the zero based indexing, I can just simply take a jump of 2 to reach to index 2, from 0 to 1 and from 1 to 2. Then what I need to do, then I will take a one jump to reach from first to reach to index 5 from the first perfect square. So plus one jump, and then I will take the remaining jump of one step. So this is simply equals to n minus 1 minus last. Cool. So if I summarize this, this is simply equals to first plus n minus last. That is first perfect square index and plus n, and minus last perfect square index. So in this case, it is simply equals to 2 plus 7 minus 5. And this is simply equals to 4. Cool. That is from 0, I can take a jump to, I can jump to 1, then from 1 to 2, then 3, 4, and finally 5. So actually it is a 7 minus 1. This one is 8. So in total it is 5. So 8 minus 5, 3, and 3 plus 2, which is equals to 5. So I hope this problem is clear to everyone. Now let's just discuss the implementation. Yeah, so here is the implementation of the first problem. So this is the method that you need to complete minimum jump with the vector points. So first I have taken n as the size of this array. Then my maximum answer will be n minus 1, when I can take a jump of one step every time. So this will be my maximum answer. And then here I have initialized first with minus 1 and last with minus 1. Then I'm iterating over all the points. And if the ith point is the first perfect square, if the ith point is the first perfect square, then I will just simply store it index, and also I will store this index in a last perfect square index. And how I'm checking whether the number is a perfect square or not? First, I'm using inbuilt function square root and finding its square root, and if the square of its square root is equals to n, then it is a perfect square. Cool. And finally, if my first not equals to last, then in that case my answer will be minimum of n minus 1, that this is how we initialize our answer, and comma first plus n minus last. So yeah, this is the complete solution. How much time it will take? This is order of n solution, and also we are using this inbuilt function, and this will take logarithmic time. So you can say n multiplied by log of points of I. So is it clear to everyone? Just write a quick +1 so that we can move to the next problem. Cool. So this is the second problem. So can transform. In this problem, you are given two strings s1 and s2 of equal length, both containing only lowercase English alphabet, that is only 26 possibilities for the characters, and you can assign a shift value, which will be a non-negative integer, to each lowercase English letter before performing any operation. And you need to perform the following operation on each character of S1 exactly once. Cool. And if the assigned integer to the character is X, then you can transform the character which is X position ahead of it or X position behind in the English alphabet in a cyclic order. For example, if you assign integer 1 to character A, then you can transform this A either to B or to Z. That is one character ahead or one character behind. And all the characters are in a cyclic order. And we need to check that if it is possible to transform S1 into S2. Otherwise, we have to return false if it is not possible. So for the first sample input, S1 is equals to Geeks for Geeks and S2 also equals to Geeks for Geeks. So for all the characters, we can select the shift value as 0. That is, we do not transform any character because both S1 and S2 are already equal. So in this case, I have to return true. Cool. Then in the second sample input, what I can do, I can assign a shift value 5 to character A, then shift value 2 to character B. So let me just quickly discuss this example here. AB, AB, then FD, FZ. So A, B, AB, then FD and FZ. Cool. So what I can do, I can assign a shift value 5 to character A, and what next we can do? Yeah, I can assign shift value 2 to character B. So what are the possibilities we have for character A and character B? So let me write the alphabets. So this is A. Then we have Z, Y, X, W, and V. Cool. So this is a fifth character behind. That is, you can either change this A to V or five character ahead. That is B, C, D, E, and F. Cool. So we have these two possibilities for A, that is we can replace every A to either V or to F, and two possibilities for character B also, that is either I can change this B to Z, or I can change this B to D. So that is Z comma D. So what I can do, I can just simply change this A to F, and this A to F, and I will change this B. Actually, it was D. Yeah, it was D. I can change this B to D, and this B to Z. Cool. You can use any character among these two characters, Z and D. So in this way, I can convert S1 to S2. So in this case, my answer will be true. I have to return true. That is, it is possible to make S1 equals to S2. Now let's just discuss another example for a more clarity. So here in this case, S1 is equals to AB, and S2 is equals to ADFZ. So S1 is equals to AB, then S2 is equals to ADF and Z. Cool. So here in this case, it is not possible to transform A into F, because for A, if you select the shift value as 5, for A, then all the character A you have to replace either with F or with V. Cool. And here in this case, if you replace this A with F, then you must have to replace this A also, either with F or with V. And both the characters not equals to the desired character at this position. So in this case, it is not possible to transform S1 into S2. So in this case, my answer will be false. Cool. So I hope the problem statement is clear to everyone. Now let's see how we can solve this problem. The solution is pretty much simple. That is, for every character S of I, for every character S1 of I have to map this S1 of I to S2 of Z. Cool. S2 of Z. I have to convert every S1 of I to S2 of I. S2 of I. And for this thing, I can just simply find the difference in their sky value. So let's say this is character A, and this is character F. So the sky value differences between these two characters is simply equals to A minus F, which is simply equals to 5. Which is simply equals to 5. If I have to convert A to F, then I must have to select the shift value as 5. Now for all the remaining occurrences of A, so let's say this is your string S1. So here we have A, then here we have A, then here we have A, then here we have A, and then here we have some other characters. Then in S2, let's say here we have this F. Here we have this F, then some character here and here. So here, if we want to convert this A into F, then we must have to select the shift value as 5. Now for all the other occurrences of A, we are just only left with the two possibility. That is, either we replace this with F, or we replace this with the fifth character behind, which was V, which was V. So I need to check whether the character at this position, this character, whether the character at this position is equals to f, or if it is equals to v, then this is an happy case. Otherwise we cannot transform s1 into s2. So in that case I will just simply return false. And if it is equals to either f or either v, then this is an happy case, and we simply move forward. So this is the complete solution, and I will do this thing for all the characters, all the 26 character. So is it clear to everyone, this solution? Just write a quick +1 if this solution is clear to you. Shreyans is saying we must choose the value which has a maximum difference. No, this is not the solution. You cannot select the maximum difference because it is constant. The shift value is constant. You cannot pick anything which is less than at the difference of 5. You must have to pick the characters which is at exactly the difference of 5, not less, not more. Exactly at the difference of 5. So this is not the maximum case. It is constant. So let me just show you the implementation. This was the complete explanation. So this is the method that you have to complete, can transform. So here in this case, I am using this unordered map, but the best is to use an array of size 26. You can also go with an array of size 26. That would also works perfectly well, and actually that solution will be the best one. So then I am iterating over all the indices. Both the characters length would be same. Then here I am finding the difference in their sky value. And if I have not inserted this difference in my map yet, then I will just simply insert this difference in my map, and then simply I am checking. Else I am simply checking whether the existing difference is equals to the desired difference. That is, this was my existing difference, and this diff is my current difference. So I will either change s1 of I to difference or 26 minus difference, because all the characters are in a cyclic order. And if both the possibilities would not equals to the desired character, that is s2 of I, so in that case I will just simply return false. It is not possible. Otherwise, after iterating over all the indices, I will just simply return true. The time complexity would be linear. Here I am assuming the best case scenario of unordered map, which is a constant time for insertion, searching, and deletion. Cool. So I hope this is clear to everyone. Now we can discuss the third problem of the contest. Good rectangles. I personally found this problem as was more tricky as compared to the fourth one. But anyway, so please try to pay more attention, especially for this problem. Good rectangles. So in this problem, you are given n cross m matrix where each cell contains a non-negative number, and you are also given two integers l and r, and a subrectangle is defined as the rectangular subgrid that can be formed by selecting any cell of the grid as the top left corner and another cell of the grid as the bottom right corner of within the grid, and a rectangle is good if the sum of numbers in all its cell is in the range from L to R, where both L and R are inclusive. And your task is to determine the number of good rectangles. So let me just explain you the first test case. So for the first test case, the value of n is 2 and the value of m is 3. And then we have 1 to 1. Yeah, 1 to 1, then 2 1 2. Cool. Then we have 1, 2 and 1. Then 2, 1 and 2. Cool. And here the value of L is 1 and the value of R is 2. So you need to find the number of rectangle, the number of sub-rectangle within this matrix whose sum of cell values is less than or equals to R and greater than or equals to L. That is within the range of L to R. So in this case, all the subrectangles of size 1 is a good rectangle. So in this case, we have a 6 rectangle of size 1. So in this case, the output will be answer is equals to 6. Cool. Now this is the second sample input where the matrix is same and the value of L is also same, but the value of R is now 11. So in this case, the value of R is 11. So in this case, what will be my answer? So in this case, all the possible rectangles are having sum in the range from 1 to 11. And how many possible rectangles we have? 18. You can count this thing. This is one rectangle whose sum is 3 less than or equals to within the range from 1 to 11. Then this is another rectangle. Then we have this another rectangle. So in total there will be 18 rectangles are there. So 18 will be your answer. Yeah, 18 will be the expected output. So I hope the problem statement is clear to everyone. So now the next thing is to analyze the constraint, which will give you an idea to how to solve this problem. So the value of n, that is the number of rows, can be up to 50 and the number of columns can be up to 1000. So the value of n can be up to 50 only and the value of m can be up to 1000. This simply means we can write some solution with the time complexity n square m. If your solution has this time complexity, then it will pass all the test cases. So let me draw some matrix here. Cool. So now let's just first find the sum of all the rectangle cell value which starts from cell 0 comma 0 and end at cell I comma j. So this is a very standard problem of dynamic programming, and having very standard recurrence relation. So let's say we have a dp of I comma j, and this dp of I comma j will simply store sum of cell values, cell values in a rectangle which is starting from cell 0 comma 0, or let's say cell 1 comma 1, as per my implementation. In my implementation I have converted everything from 0 comma 0 to 1 comma 1, just to avoid handling the edge cases, and ends at cell I comma j, cell I comma j. So let's say this is cell 1 comma 1, and all right, so let's say this is our cell 1 comma 1, and let's say this is I comma j. This is my cell I comma j. So I need to find the sum of cell values in this rectangle. So for this thing, I can just simply add. I can simply add this area. I can add this area, and then I can add this area, and then I will just simply subtract this overlapping sum. This is a very standard reconciliation. Then I will just simply subtract this overlapping segment, so that I can get the desired rectangle. So dp of I comma j, dp of I comma j, it is simply equals to, this is simply equals to grid of I comma j, that is a current cell value, and plus this upper rectangle value. So dp of I minus 1 and j. Cool. That is previous column, previous row, same column, plus this left rectangle value. So dp of I comma j minus 1, and then I have to subtract this overlapping part. So minus dp of I minus 1 and j minus 1. And before moving to cell I comma j, I already know these also. I already have these also. So in this way, I can find the sum of cell values in a rectangle starting from cell 1 comma 1 and ends at cell I comma j. So now after this, how I can find the answer? So there was a connection issue from my end, and really sorry for that. Hopefully it is fixed now. So let's just get back to the solution where we are. Yeah. So dp of I comma j, sum of all cell values in a rectangle starting from cell 1 comma 1 and ends at cell I comma j. So with this recurrence relation, in this recurrence relation, I can find find the value for every I comma j. Cool. And then after this, how I will find the exact answer. So now please try to pay more attention. This is very important. So for this thing, what I can do, I can fix I comma j as starting index as a top left corner of a rectangle. So let's just fix every I comma j as a top left corner of the rectangle. So let's say this is I comma j, I comma j. Now this is I comma j. I have fix I comma j, and if you fix this I comma j, then I need to count, that is find a number of rectangles starting from cell I comma j, that is this I comma j as the top left corner of the rectangle, and sum of cell values are in the range from L to R. Cool. And how I get this thing? Because there can be many rectangles. Let's say this rectangle, which starts from I comma j, is having some less than some in the range from L to R. Then this is another rectangle. Then this is, let's say this is another rectangle whose cell values is in the range from L to R. So I can just further simplify this problem. So from here I can just simply say it is equals to count. This count is a function that will return me the number of rectangle starting from cell I comma j and having sum less than or equals to R. And if I know all the rectangles whose sum is less than or equals to R, then I can just simply subtract the number of rectangle whose sum is less than or equals to L minus 1. So that now I know the number of rectangles whose sum is in the range from L to R. This is simple inclusion exclusion principle. So how to get this thing? So for this I can apply a binary search. Now I have fixed the top left corner. This is my top left corner of the rectangle, and then what I can do, I can just simply iterate. I can simply iterate over all the rows starting from this I. So for every I will iterate over all the previous cell in the same row. That is this row. Let's call this integer as row. Cool. And it starts from I and goes till n. That is to the last row. And now you know that your left boundary is fixed. Now I need to check. I need to find the column number. So what will be my column number? So this will be my range of columns, that is possibilities for column. And here I will just simply apply a binary search. And why I am saying that I have to apply a binary search? So let's say, so here I will iterate over these values. So this is from I 2n. And let's say this is my current row. Let's call this as row. Now here I need to find the maximum column number. So with the help of a binary search, I have to find the maximum column number. Maximum column number. Cool. And why binary search? Because let's say this rectangle, if this rectangle is having some, let's say this rectangle is having some greater than r, then all the rectangles, that is all the remaining columns which is on a right of a current column, will also having some greater than r. That is, this rectangle will also have some greater than r. This rectangle will also have some greater than r. So that's why I need to find the maximum column number, so that the sum is less than or equals to r. And here why I'm saying r, because currently I'm solving for this one. I'm solving this function. If you are solving this, then we need to find the column number for which the sum is less than l minus 1, less than or equals to l minus 1. So at this point of time, let's just only focus on this limit as r, because both the functions will be same. There is only change in the limit. So that's why we can simply apply a binary search to get the maximum column number. Maximum column number where value is less than or equals to this limit. For the first time, the limit is r. For the next time, the limit is l minus 1. Cool. And how you will get this thing? So let's say this is your column number that you have fixed, that you have decided. So let's say this is the column number that you have decided. Let's call this as m. Yeah, because we I will find this mid value, because we are applying the binary search. Now how I will get this thing? How I will get the sum of cell values in this rectangle. So this is simply equals to dp of row, that is this entire sum. So row, and you also know the column number. So this is simply m. Cool. And from here I have to subtract this thing. I have to subtract this area. And I have to subtract this area. And since this is an overlapping segment, so I have to add this area, the value of this area. I have to add it once. So this is simply equals to dp of row m minus dp of I minus 1. And basically this is a left for the above rectangle. So I minus 1, that is a previous row, and same column m. Cool. And then for the left rectangle, this is simply dp of m, not m, but dp of row and j minus 1. Cool. That is same row, previous column. And I have to add this overlapping segment. So dp of I minus 1 and j minus 1. And if this sum is less than or equals to r, then simply update the value of low in a binary search, and also store this index, store this value of mid, because this might be the case. This might be the maximum column number. So this is the complete solution. Is it clear to everyone? And what will be the time complexity in this case? In this case, the time complexity is n into m, that is for different values of I and j, and then I am iterating over the remaining rows from I to n. So another n, and multiplied by some log, because we are applying a binary search. So this is log of m base 2. because we are applying a binary search to get the maximum column number. So this is the complete solution, and I hope it is clear to everyone. Now let me just show you the implementation. So yeah, here is the implementation. This is the method that you need to complete. Count good. So here first I'm updating this, I'm creating this DP 2D vector of size n plus 1 and m plus 1. I have just converted to a one base indexing to avoid handling the edge cases. So then I'm filling this DP table, and then I iterate over all the values of I and all the values of j, that is fix I comma j as the starting cell of a rectangle. Then I iterate over all the rows starting from I to n. Cool. And here first I'm simply adding count of r, and then I'm subtracting count of l minus 1, so that we get the number of rectangle in the range from l to r. Cool. And here I have passed this row also, current row. Then this is the method. This is a method that will return me the number of rectangle whose value is less than or equals to the given limit. So then I'm first counting the number of rows, and then I'm counting the number of columns and subtracting one because I have created of one bigger size. Then this will be my low, the area, the range where we have to apply a binary search. So the minimum column number, which is the current column j, and the maximum column number m. Cool. And then here I'm simply counting the number of rectangle whose value is less than or equals to the given limit, then finding mid. Then this will be my rectangle sum, and if this sum is less than or equals to mid, then here I'm updating the value of count, that is number of rectangle. So this is simply equals to mid minus j plus 1. Cool, because mid and j both are inclusive. And then I'm updating the value of low, and else I'm updating the value of high, and finally I'm returning this count. So what is this thing, mid minus j plus 1? Because if this is the last rectangle which is satisfying the condition, then this rectangle will also have sum less than or equals to limit, and this rectangle will also have the sum less than or equals to the limit. So this is simply equals to m minus j plus 1. Cool. So I hope it is clear to everyone, and we have already discussed the time complexity. So just write a quick plus 1 if this approach is clear to you. Cool. So now let's just finally discuss the last problem of the contest. Minimum area of a rectangle. So in this problem, Geek is given a string path consisting of a characters U, D, L, and R, and these character represents the moment in a 2D grid whose dimension will be not given to you, and you need to find its dimension. So where the top left corner is 0, 0, cell 0, 0, obviously, and the character D simply means move one cell down. Then character U means move move one cell up, then R means one cell right, and L means one cell left. And initially Geek is standing at cell L 0, 0 in a rectangular grid of size n cross m, where n represents the number of rows and m represents the number of columns. And note that n and m are not provided as an input and must be determined by you to satisfy the condition as described. Geek must follow the movement in the path string in the same order. However, if at some point of time Geek step outside the boundary of the rectangular grid, he remain in his current cell instead of moving. And the final cell f of r, comma f of c, that Geek must reach by following the entire path. And you need to determine the minimum possible area of a rectangle n cross m that allows Geek to complete the path to reach to the destination f of r comma f of c at the end. And if it is not possible to reach at this target cell, then you have to return -1. So let's just discuss some examples so that it will be more clear to you. So for the first example, the given path is d d, then r r, and the destination cell, that is f of r comma f of c, this is equals to 1 comma 2, 1 comma 2. Cool. So what I can do, I can just simply consider the value of n, that is a number of rows, as 2 and the number of column as 3. So the number of rows as 2 and the number of column as 3. So 2 comma 3 will be its area. So this is my target. So column 0, column 1, column 2, then row 0, row 1 and row 2. So this is my target. So actually I have created 3 rows. It was my bad. So 2 cross 3. So this is my target, 1 comma 2. So how I can reach here? So initially I'm standing at here. Initially the person is standing at here. Then from here I can just simply follow this path, that is move downwards. I can reach to this cell 1 comma 0, and then I again have to move to downward, but it is not possible since we are at the boundary cell. So here in this case, do not perform any operation, do not perform any move, remain at the same at the same cell, or you can say skip this step. Then the next one is right, move one cell right, which is 1 comma 1, and then again move one cell right. So now we have reached to the destination. Now we have reached to the destination, and your answer will be equals to the area of this rectangle. So which is 6. Here I have selected the value of n as 2 and the value of m, that is number of column, as 3. So I hope the problem statement is at least clear to everyone. Now for the second sample test case, it is not possible to reach to the desired target cell. So in this case your answer will be -1. So now let's just quickly discuss the problem. And this is a easy problem as compared to the last one, the third problem. So now some of you might wondering. Now please try to pay more attention. So some of you might wondering why we need to create the rectangle of some greater size, rectangle of some bigger size. Because if I know the starting point, if I know the starting point and if I know the target, then I will just simply create a rectangle with the dimension f of r plus 1 multiplied by f of c plus 1. But this is not always possible, because you must have to reach to the destination. And there might be the case when you require a rectangle of some bigger size. So let me just give you a counter example where it is not where you do not have to create the rectangle of the same size. You have to create a rectangle of a bigger size. So let's say the given string, that is path, is equals to d, 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 and d. And let's say then we have operation u and then for operation of right. And also let's just say our target cell, that is f of r comma f of c, f of r comma f of c, as 2 comma 2 comma 2. Let's just say this thing. So in this case, what you will say that what you will do, you will say that I will create a rectangle, or it is actually a 3 comma 3. Let's say this is 3 comma 3. So in this case, you will say that I will create a rectangle with the dimension 4 cross 4. So let's just do it. 4 rows and 4 columns, because I know the starting point, I know the destination, I know the target cell. So how it is optimal to create a rectangle of some bigger size? So this is a column 0, column 1, column 2, column 3, then row 0, row 1, row 2, and row 3. Cool. So this is my target, that is 3 comma 3. So in this case, will it be possible to reach to the destination by following this path? So initially you are standing at here. Then you will perform this operation, and you will move to the cell one cell down, and basically I have used this operation, then this one, then you will move to this cell. So currently we are at 2 comma 0, and then you will perform this operation, and you will move to the cell 3 comma 0, and then you got this operation. But you cannot perform this operation since you will be at you are at the boundary cell. Then the next operation, which is u, I will perform this operation, and now I have reached to this row, that is row 2. This is not same as the desired row. My desired row is this one. My desired row is row 3, and since after this I do not have any operation of d, so I cannot reach to the desired row. So now I have to perform this operation r. So to this one cell right, then again operation r, one cell right, then again operation r, one cell right. So now I have reached to the desired column, but I have not reached to the desired row. So in this case, I have to create a rectangle of a bigger size. So what I'm trying to say, instead of selecting the value of n, as 4 and the value of m as 4, let's just select the value of n as 5. So here I am selecting the value of n as 5. So now let's see if it is now possible to reach to the desired cell or not. So now it is possible. So let's just again perform the operation. So initially you are at 0, 0, then operation D, then again operation D, then again operation D, and then again operation D. Cool. And then operation U, that is we are at row 3, and then operation R, then operation R, and then finally operation R. Now I have reached to the desired cell, and the value of n, the minimum value of n is 5, and the minimum value of 4, the minimum value of m is 4. This will be my answer. So I hope the logic is clear to everyone. Now let's see how we can solve this problem. So this also gives you idea to apply a binary search. What I am trying to say, if this is my best value of n, that is the minimum n is equals to 5, then it is also possible to reach to the desired row by selecting the values of n greater than 5. So that is, if you select the value of n as 6 as 5, so this is actually 5, and if you select the value of n as 6, then also you will reach to the desired row, because after 3 you will move to this 4, and then after this you will again go back to the 3, and if you select the value of n as 6, then also you will reach to the desired row. So if it is possible to reach to the desired row by selecting the value of n as 5, then you will also reach to the desired row by selecting the value of n as 6, value of n as 7, and for all the values greater than 5. So this is a monotonic predicate nature. So this is my n, and then n plus 1, the minimum n, then n plus 2, then n plus 3, and so on, then n minus 1, n minus 2, n minus 3, and so on. So if my binary search or check function is returning true for n, then it will also return true for n plus 1, also return true for n plus 2. That is, it is possible to reach to the desired row. Then true for these, and false for n minus 1, false for n minus 2, false for n minus 3. And we need to find the minimum value of n for which the check function is returning me true. So this will be my answer. That is, n is equals to 5. And the same argument we can use for a column. Cool. So with the help of a binary search, you can find a minimum n and a minimum value of m. And what will be my ranges? So the value of L is 0, and the value of R, that is the value of high. What will be the value of high in this case? So value of low is 0, and the value of high, this is simply equals to the number of down characters that we have. So I is equals to 0, and it goes till the length of the string. Let's call this a string, path string, as s minus 1, and the number of characters which are equals to d, because these many rows we can reach in the best case when we all have the down character, and if we got some up character, then it will cancel out one down. In the best case, we can reach to these many rows. And similarly, the same argument you can minimum m value, that is minimum column value. And for n, you just only have to consider the operation down and up, and for m you have to consider the operation left and right, because these two are related with each other, d and u, and l and r. There is no relation between l and d or l and u. So if there is some doubt, then it must be clear after discussing the implementation. So yeah, here is the implementation. First, I'm counting the number of down characters that we have and the number of right character that we have to apply the binary search. This will be my boundary. And first, I'm finding the minimum row. And for this thing here, I have initialized n with the -1 and low as 0 and row high as a down count. Then here I'm finding this mid, that is the value of n. And if after considering the value of n as this row low plus row high divided by 2, if it lead to my desired row, that is if final row is equals to f of r, ffr, then this can be my n. So I am storing this value of mid and updating the value of high, because we need to find the minimum n. Cool. Else these are the else case. And the same thing I'm doing for the column. And after this, let me just show you this function, this get row function. So this get row function, so initially I'm at, say I am at row 0, and then I iterate over all the characters of the path, and if the character is d and if the position is less than n, because here n is the maximum column number, maximum row number that we can have. So if the position is less than n, then we can just simply increment the position. Otherwise we just simply decrement the position. If it is u and the position is greater than 0, that is you are not at the boundary cell, so just simply decrement it. And finally I'm returning this position. Cool. And the same I'm checking for the column. If it is r, then increment the position. If it is l, then decrement the position. And then finally I'm checking if the value of n is -1 and the value of m, or the value of m is -1. That is if either it is not possible to reach to the desired row, or if it is not possible to reach to the desired column, then in that case my answer will be -1. Otherwise my answer will be equals to its area, that is n plus 1 multiplied by m plus 1. So yeah, this was the complete solution for all the 4 problems, and now we are good to wrap the session. So thank you so much guys for joining the session, and also you can leave your comments so that I can improve myself for the more upcoming analysis. And if you have learned something new, then please hit the like button. So thank you so much and have a good day.